Good morning everyone. Once again I am Aamir sir present in front of you with the last lecture, that is lecture number 16 of chapter solid state. Today we will study about the sum up of this chapter solid state and few of the new things which you are not knowing, and that is very important from examination point of view. So let's begin with the first topic of today, that is the characteristics and examples of different crystal system. We have already seen, let's see it again. So here the heading is characteristics and example of different crystal systems. So crystal, hexagonal close packing, cubic close packing, face centered cubic close packing, or body centered cubic close packing. So if it is hexagonal close packed structure crystal, what will be the space occupied? That will be 74%. What will be the vacant space? So 7400 minus 74, 26%. What will be the coordination number in case of SCP? It will be 12. So you have to remember the type of crystal, space present, coordination number, and example is also important. It can come in one word, that what will be the example of SCP among these. So molybdenum, magnesium, beryllium, cadmium, zinc, titanium, solid helium, solid hydrogen. So these all atoms or metals comes under the example of SCP type of crystal, which have coordination number 12, space occupied is 74. Second one is CCP or FCC is same. So cubic close packing or face centered cubic close packing is same. So that also have space occupied 74%. Coordination number is also same, like SCP and CCP have same space occupied and coordination number 12. And examples are iron, nickel, copper, silver, aluminium, all solid noble gases. So all the solid noble gases are the example of CCP or FCC closed packed structure, except helium. So helium comes in SCP crystal, but rest of the noble gas comes in CCP or FCC crystal. So solid methane, same way solid HCl and solid H2S. So all are the example of CCP or FCC closed packed structure having coordination number 12, packing fraction 74%. Third one is BCC, body centered closed packed structure, have space occupied 68%, that is the packing fraction, and coordination number is 8. Examples are all the alkali metal, Li, Na, Ke, Rhapsus. So lithium, sodium, potassium, rubidium and cesium are the example of BCC crystal, have their coordination number is 8. So if the question come, what will the coordination number of lithium? So we will give answer 8. Sodium will say 8. Now what is the relationship between the radius of octahedral void, which is shown with R0, and atom having closed packed arrangement? Let's see. In ionic compound, octahedral void is formed when 6 anion form a regular octahedron. That is, 4 anion are placed in one plane, and one is placed in depression above this plane, and one is placed depression below this plane. Just focus on this structure. So these are the anions. 1, 2, 3, 4. Anion means negative charge ion. They are bigger in size. Anion having closed packed structure. Radius of anion is shown with small r minus, So these are the four anions, and at the center is cation, that is small in size. Cation occupy octahedral void. So octahedral void, how the octahedral void is formed? It is formed by the 6 touching particles, 6 touching atoms. So these are the anions 1, 2, 3, 4. Above the cation there is one more anion, and below this cation there is one more anion. So 6 anions are touching with this cation, which has occupied the octahedral void. We say octahedral, but it is in contact with 6 atom only. It is formed with 6 atom only. So don't get confused with the word octa. Octa here stands for 6 touching atoms, and these 6 touching atoms are the anions, which are bigger in size, and this cation, positive ion, is present in the void of that 6 anions. So now cation occupy octahedral void. Radius of cation is shown with r plus, which is equals to radius of octahedral void, r0. So octahedral void and the radius of cation are equal, because that octahedral void is present at the center. Cation is also present at the center at the place of octahedral void, forming octahedral void. So therefore the radius of cation R plus is equals to the radius of octahedral void R naught, means R plus is equals to R naught. Now octahedral voids thus formed is occupied by a cation, at the center, is occupied by a cation, a small circle, that is shown with small circle, and four anions bigger circle, this one, four anions lying in one plane have been shown. The anion lying above and below the small circle, that is the cation at the center, is not being shown, so that we are not showing it. The radius of cation R plus is equal to radius of octahedral void R naught, because they both are at the same place at the center. So radius of cation whether with the radius of octahedral void, they are same. So both their radius is same. Since cation exactly fits in the octahedral voids, therefore R plus is equals to R naught. The relationship between R plus or R minus and R naught be found by considering right angle triangle ABC, in which angle ABC is equals to 90 degree. So see in the picture. So here it forms A, B and C. So this ABC forms a 90 degree right angle triangle. So this ABC, angle ABC is 90 degree. So that leads to the formation of B forming the radius R minus, A forming radius R minus, C forming radius R minus, because R minus is your anion, and at the center cation is present. That cation is present, showing R plus, that is the diameter of that cation. So it's the same is shown here. The relationship between R plus or R minus and R naught be found to be considering right angle triangle ABC, in which angle ABC is 90 degree. Thus we get AC equals to what? AB square plus BC square. So just you get the calculation, you will get that by Pythagoras theorem. Therefore at AC, what we have? AC, this line AC. So that AC consists of R minus at the center, R plus. So R minus plus R minus 2R plus. So therefore R minus R plus and R plus, that is R plus, not T, that is R plus. So we get finally that, and under root AB square will be R minus plus R minus square. Just go through that figure. And BC is also R minus plus R minus square. So finally we'll get that R plus is equals to 0.414 R minus, and R naught is equals to 0.414 R minus, because R plus or R naught are same. So therefore R plus is equals to 0.414 R minus, or R naught is equals to 0.414 R minus. So that you have to remember that what is the relationship between the R plus and R minus, or R naught or R minus. Now the ratio between radius of tetrahedral void RT and that of the sphere R forming the structure is equals to 0.225. So that is a calculated value, that the ratio of what? Radius of tetrahedral void T, that is shown with RT, divided by radius of sphere, and that of radius of sphere is shown with capital R. So RT by R is equals to 0.225. So the radius of tetrahedral void comes to be equals to 0.225 R, that is the radius of sphere. So that is giving the relationship between tetrahedral void and the radius of sphere, that RT is equals to 0.225 R. Next, the ratio between radius of octahedral void R naught and that of the sphere R forming the structure is equals to 0.414. So first we have seen for the tetrahedral void relationship with the radius of this sphere. Now we have relationship with radius of octahedral void R naught by R, that is equals to 0.414 calculated value. Therefore R naught is equals to 0.414 R. Next, If cation of an ionic compound occupy tetrahedral void, if cation of an ionic compound occupies tetrahedral void, then radius of cation RT is equals to 0.225 into radius of anion forming the closed packed structure. So it gives the relationship between the radius of cation with the radius of anion. So what is the relationship between radius of cation and radius of anion? So radius of cation is equals to 0.225 into radius of anion. So RT is equals R plus. So radius of cation is shown with plus sign and anion with R minus. So R plus is equals to 0.225 into R minus. So that is the relationship between radius of cation and the radius of anion. So if cation of an ionic compound occupy octahedral void, then what will be the formula? So in case of tetrahedral, we use 0.225. In case of octahedral void, we'll use the value 0.414. Rest thing will be same. So RT will be equals to R plus. Sorry, R plus is equals to 0.414 into R minus. So one numerical is there based on it. So in a crystalline solid, the atom A and B are arranged as follows. A, atom A arranged in CCP arrangement, CCP, cubic close packing. Second one, atom B occupy all the octahedral void. So atom B is occupying all the octahedral void and half of tetrahedral void. Now question asks, what is the formula of the compound? So how will we get the formula of the compound with this data? So there is a solid having atom A and B arrangement as follows. So if number of atoms are arranged in CCP arrangement, that is A atom, so we'll consider number of atom arranged in CCP for A is equals to small a. Then number of octahedral holes will be what? So if the void says octahedral void, then we know that it is half of tetrahedral void. So if octahedral void is considered as small a, so it is written then number of octahedral hole is equals to small a, and number of tetrahedral hole will be double of octahedral void holes, so it will be 2a. If the octahedral hole is a, then tetrahedral hole will be 2a. What is a? Number of atom arranged in CCP arrangement is a, that is equals to number of octahedral hole a, and if there is tetrahedral hole, it will be double of octahedral hole, that is 2a. Now these holes are occupied by B atom. Number of B atom occupying all octahedral hole equals to a. Number of B atom occupying half of a 2a tetrahedral hole. So half into 2a, or in case of octahedral it is a only, but in question it is given for tetrahedral it is half of tetrahedral hole. So therefore half into 2a, tetrahedral hole is 2a. So therefore we'll get the value a. So therefore total number of B atom occupying all octahedral holes and half of tetrahedral hole, that is a, and this of a also, a plus a, it gives 2a. Therefore number of A atom ratio to number of B atom is, in A that is only one atom, A small a, ratio of number of B atom is 2a. So formula of the compound will be A small a B 2a, or we can write A B2. You have to note, in ionic compound it is found that anions, large ion, usually have cubic close packs. So anions have CCP structure or SCP arrangement, and cations, small ions, are present in octahedral or tetrahedral void. So you have to keep in mind, whenever there is the cation, it will be the void. It is present at the void's position, whether it can be the octahedral or tetrahedral, or octahedral. If it is anion, it forms always cubic close packed structure or SCP arrangement. If it is cation, small ion, it is present always at voids, octahedral or tetrahedral. But it is not necessary that all the tetrahedral and octahedral voids are occupied by the cations. So it is also said that the cation voids can be vacant also, but if the voids is occupied, it will be occupied by the cations only. Anions have CCP structure, so they are never found in the voids. Now coming to the ionic crystal. So ionic crystal, how will get the ratio, radius ratio of ionic crystal, Na plus Cl minus. So there is formula that radius ratio is equals to radius of cation R plus divided by radius of anion R minus. Radius ratio of ionic compound will be radius of cation A plus divided by radius of anion B minus, that is equals to Ra plus divided by Rb minus. Now that is very important to remember to get the many questions answer. Radius ratio rule for AB type structure. AB means NaCl, KCl, like that. So radius ratio, if the value comes of radius ratio in range 0.155 to 0.225, then the coordination number of that structure will be 3 and structural arrangement will be planar triangular or triangular planar. And what will be the example of such type of structure? That will be B2O3, boron trioxide. So if boron trioxide is there, its radius ratio comes in this range, its coordination number will be 3 and the structure will be triangular planar. Same way, second one, if the radius ratio comes 0.225 to 0.414, then such types of structure have coordination number 4 and have structure tetrahedral. Examples of such types of crystal will be ZnS, phallerite, or copper chloride, copper bromide, copper iodide, or barium sulfide. Even HGS, hydrogen sulfide, have tetrahedral arrangement having coordination number 4 and their radius ratio comes in this range. So we will get it, we confirm that they have coordination number 4 and have tetrahedral structure. Third one, if radius ratio comes in range 0.414 to 0.732, its coordination number will be 6, structure will be octahedral. Very important, the structure of NaCl, that is also called rock salt, have coordination number 6, structure octahedral in their crystal. Other examples showing this type of structure are sodium bromide, potassium bromide, magnesium oxide, calcium oxide, manganese oxide, calcium sulfide. The last one is 4 numbers 0.732 to 1. If the radius ratio comes in this range, it confirms that have BCC structure. Coordination number will be 8. Examples are cesium chloride, cesium iodide, cesium bromide, thallium bromide, ammonium bromide. Show these types of packing having coordination number this and radius range comes in this. Have the numericals based on this. Question number 1. Two ions A plus and B minus have radius 88 and 200 picometer in close packed crystal, so CCP crystal of compound AB. Predict coordination number of A plus. So you have to tell what will be the coordination number of A plus. So first thing is to get the radius ratio to know in which range they comes. So R plus by R minus, that is R A plus by R B minus, value is given for A plus 88 and for B minus 200 we get 0.44. So you have to see in which range they come. 0.44 falls in which range? So 0.44 falls in third one, 0.414 to 0.732. It means that it is written it lies in range of 0.414 to 0.732. Hence it has coordination number. A plus have coordination number how much? Then 6. So 6 will be the answer. Same way, question number 2 we have. An ionic solid AB has sodium chloride structure. If radius of cation is A plus is 100 picometer, what will be the expected radius of an ion? So it is asking for the radius of an ion expected. The answer is the ionic solid is expected to have octahedral structure. So how we come to know that they have octahedral structure? So if it is NaCl, just reverse it, we'll see get the answer. If it is NaCl, so where is NaCl? So NaCl is here, so you have to remember it. So NaCl has which type of structure? Octahedral, and have coordination number how much? 6. Value of radius this much. So by knowing NaCl we can get this 3 answer. So same way we have find out this one, that they are asking for the expected radius of an ion and NaCl was there. So NaCl which type of crystal they have? So octahedral structure. So if it is octahedral, in which radius range they comes? So they lies in 0.414 to 0.732. So therefore radius of an ion may be, so R plus by R minus, the value expected value is this, both will write there. So or R minus will be equals to R plus divided by this value, 100 divided by this value. So because we have to get the what is the expected radius, thus radius of cation will be in range that comes if we'll take this value, this gives, if we take 0.41, 100 divided by 0.414, we get this one. If we get 100 divided by 0.73, we get this one. So the radius of cation will range from this to this picometer. Third question, if the radius of bromine ion is 0.182 nanometer, how large a cation can fit in each of the tetrahedral voids? So radius of an ion is given, Br minus is given. Now it is asking for the radius of cation that can fit to tetrahedral voids. So cation always fits to void, whether it be tetrahedral or octahedral. So we'll first go with, for a cation to fit in tetrahedral void, the value of R plus by R minus should be, so for fitting in tetrahedral void. So how we have get this value 0.225 to 0.414. So again we'll go to that structure. So where is tetrahedral? So tetrahedral means the value of R will be this. You have to remember this 0.225 to 0.414. So same value is taken here. 0.225 to 0.414. Apply the formula R plus by R minus. R plus we have to get. R minus is given, and the value is equals to 0.225 to 0.414. Expected value comes in this range. So by applying the formula first to R plus 0. Br minus value is given 0.18182. So apply this first to this one, then to this one. What will get? By applying to R plus 0.182 to 0.225, we'll get R plus equals to 0.040, smallest value. And if we take R plus divided by 0.182 equals to bigger one, that is this range, 0.414, R plus will be equals to 0.075, largest value. So question was asking for the what? Question was asking for the radius only. What is the radius of largest cation? So for largest cation we have to take largest value. So the largest cation that can fit in tetrahedral void will have radius 0.075 nanometer. One more question. Question number 4. The hematite Fe2O3 consists of cubic close packed arrangement of oxide ion with Fe3 plus ion occupying interstitial position. Predict whether the iron ion are in octahedral or tetrahedral void. So radius of Fe is given and that of O2 minus is also given. Apply the formula radius ratio of Fe2O3 value R plus by R minus, that is Fe3 plus by O2 minus, so gives 0.45. So this 0.45 comes in which range? The value of range comes in 0.414 to 0.732. Since the value lies in range of this, so Fe3 plus cation will occupy octahedral void. How we come to know that they occupy octahedral void position? That relation is given already there, that if it comes in 0.414 to 0.732, which types of void they occupy? That have octahedral. So we come to know that they have octahedral elements. So since the value lies in range of 0.414 to 0.732, therefore Fe3 plus cation occupy which void? So octahedral void. Last question is question number 5. Calculate radius ratio of alkali metal bromide on the basis of data given and form of the crystal structure in each case. Ionic radius is given: lithium ion, sodium ion, potassium ion, bromide ion. All radius ratio is given. So compound is lithium bromide. So what will the value of R plus or minus? So 74 divided by 195, the value is given in question for both. 74 divided by 195, we get 0.379, and that comes in range of, you can see in that page, so it comes in range of 0.379. See in which range they come: 0.379, 0.225 to 0.414. What will the coordination number? 4. What will the structure? Tetrahedral. So see here, so so coordination number is 4. Type of structure is FCC. So face centered cubic crystal they have. Lithium ion cation occupy alternate tetrahedral void. Same way sodium bromide value comes coordination number 6, FCC crystal. Sodium occupies octahedral void. So it depends on the value, what is the value given. So based on that we decide the voids, which types of void, what is the coordination number, what is the type of structure. So potassium bromide, 0.708, coordination number value is 6. You just check it from that way. And have FCC structure, K plus occupy octahedral void, rubidium bromide, same way, value comes coordination number 8, type of structure occupy BCC, same way cesium bromide, value comes this, coordination number 8, type of structure occupied BCC. So with this way we have completed till here. Now the last topic which I will focus here, that is very important from examination point of view. Summary of the structure of ionic solid, compound description, coordination number, other examples. So first one is sodium chloride. So sodium chloride have CCP cubic close packed arrangement of chlorine minus Na plus in all the octahedral sites. So Na plus is present in octahedral void and chlorine minus is occupying CCP. Sodium plus have coordination number 6, chlorine minus has coordination number 6. Other example is lithium, sodium, potassium halides, AgCl, AgBr, MgO, calcium oxides. So these are the example have coordination number this. Second one, zinc sulfide, that is also called zinc blende. So here also sulfide occupies CCP, cubic close packed arrangement of S2 minus and Zn2 plus metal ion are present in alternate tetrahedral sites. So Zn2 plus has coordination number 4 and S2 minus has coordination number 4. So HES, helium sulfide, calcium chloride, copper bromide, copper iodide are the example of this type of structure. Third one is cesium chloride. So simplest cubic structure, cesium has coordination number 8, cesium bromide and cesium iodide has also coordination number 8. Calcium fluoride, so CCP arrangement of Ca2 plus, F minus occupy tetrahedral site. So just opposite in this case, that F minus occupying tetrahedral void, Ca2 plus has coordination number 8, F minus has coordination number 4 in CaF2. Other example are SRF2, BaI2, CaF2. Last one is sodium iodide, NaO. CCP structure is occupied by oxygen, Na plus occupied tetrahedral side, Na have coordination number 4, oxide has coordination number 8. Other examples are Li2O and K2S. So it will be Na2S. It will be Na2S. So till here we have completed the chapter. Till here we have completed. Just note it down, this all things, and we'll visit in next chapter. Any doubt, any problem you can ask.